Respected Professor G. Srinivasan sir, who he has kindly agreed. Thank you, sir. Thanks for agreeing and gracing the occasion. Professor Srinivasan sir, actually he obtained his PhD from the University of Chicago in 1970. And more importantly, there, you know that one great person of eminence, Subramanian Chandrasekhar, was also at University of Chicago. And Professor Srinivasan sir has worked with him. And he also worked at IBM Research Laboratory in Zurich, Switzerland. Then he was for a long time with Raman Research Institute. And he is a fellow of Indian Academy of Sciences. He is Professor Srinivasan is a fellow of the Royal Astronomical Society, London. He is the past president, Astronomical Society of India, and past president, Division on Space and High Energy Astrophysics, International Astronomical Union, IAU. He is a member of the Apex Science Board of ISRO, which decides about the space science missions of ISRO. And since his retirement in 2004, he has been very active in public outreach activities. Sharing your knowledge is very important. All of us think that we know a lot, but sharing it with others, okay? And communicating it in a way which can be understood, and it should be capable of inspiring others. That is very important. And in that, for the past 20 years, specifically after his retirement, Srinivasan sir is active. And thank you very much, sir. A person of this eminence has graced us. And thanks, sir. Thanks once again on behalf of JNP for coming here and delivering the talk. Now I request Sharanya to hand him over a small memento, sapling, on this
Thank
occasion.
you very much.
Thank you.
It's very nice. This is our universe. If you look really deep, deep, deep into the universe, this is what you see. Now come with me on a journey through our universe. What are the building blocks of the universe that we just had a journey through? The building blocks are clusters of galaxies, such as you see here. Every bright spot on the screen is a galaxy, and a cluster of galaxy has about several thousand galaxies bound together by mutual gravity. A typical galaxy, such as this one, has a million stars. How big is our universe? As was mentioned a few minutes ago, at the turn of the 20th century, the great Dutch astronomer Kapteyn tried to map the universe with the facilities that were available to him 120 years ago. And that is the map of the universe as he produced in 1910. What is interesting about that map is that the universe at the time was synonymous with our Milky Way galaxy. And most disturbingly, the sun was at the center of the universe. The universe was only 40,000 light years in size. A light year is the distance light travels in 1 year. It's roughly 10 million kilometers. So the universe was very small. When you look at the sky with a large telescope, you see not only stars, but here and there you see nebular objects such as this, objects that look like an omelette or a fried egg. And at the turn of the 20th century, there was a great debate as to the nature of these nebular objects. Some people thought that these nebular objects were inside our galaxy, whereas others thought that they were outside our galaxy, and indeed they were galaxies in their own right. The American astronomer Edwin Hubble in 1923 made a very profound discovery which enabled him to measure the distance to this nebula that you see in the constellation Andromeda. It was known as the Andromeda Nebula. And the distance turned out to be 3 million light years. Surely that is a much larger distance than the size of our galaxy. Therefore, it became clear overnight that these nebular objects in the sky were island universes like our own galaxies. And in the next 3 or 4 decades, the universe dramatically expanded in size. So there was not just the Milky Way galaxy, there were other galaxies. It turns out that there are more than 350 billion large galaxies, each galaxy containing a million stars. As for the building blocks of the universe, the clusters of galaxies, there are more than 25 billion clusters of galaxies. Now, what you see in this slide is the large-scale architecture of the universe. Every dot that you see on the screen, they are not stars. They are not even galaxies containing millions and millions of stars. Each dot is a cluster of galaxies or a cluster of galaxies. So that is the scale of the universe that we are going to talk about. The topic that I was asked to talk about was the origin and evolution of the universe. Now let me first say something about the nature of cosmology, which is the study of the universe. Cosmology is a very different science than anything else in physics or chemistry. Cosmology is a theory about a theory. We first theorize that the universe must have evolved, and then we construct a theory of a possible evolution. In that sense, there is only one other theory that I know of, and that is Darwin's theory of the evolution of species. Darwin hypothesized that there must have been evolution. And then he constructed a theory of such an evolution, namely evolution through natural selection. So cosmology is a theory about a theory. And then you look for observational evidence like Darwin did to validate this theory about the theory. So once that is clear, we have to ask, what is the theoretical framework within which you can study the universe? It turned out that till 1915, we did not have a theoretical framework to study the universe at large. Newton's theory was not adequate because in case the universe was infinite, Newton's theory was not capable of dealing with the infinite universe. Einstein's general theory of relativity provided for the very first time the theoretical framework to study the universe at large. And this theory was published by Einstein in November of 1915. Soon after that, in 1922, a young Russian mathematician by name Alexander Friedman showed that if Einstein's theory was correct, and if the universe is homogeneous and isotropic, what do I mean by that? It looks the same in all directions, and it looks the same everywhere in the universe. So if the universe was homogeneous and isotropic, then Friedman pointed out that within Einstein's theory, the universe cannot be static. The universe has to either expand or it must contract. So I hope that I made that clear. Einstein himself thought in 1917 that the universe must be static. But Friedman showed in his own theory that using Einstein's theory, that the universe cannot be static, it has to either expand and contract. Einstein rejected this conclusion, and the paper by Friedman was unfortunately sent to to Einstein for refereeing, and Einstein withheld the publication of paper for 2 years. It turned out that Einstein was wrong because our universe is not static, it is in fact expanding. The first evidence for this came in the year 1912 when the American astronomer Westo Slipher discovered that spectral lines from galaxies were systematically shifted to longer and longer wavelengths. Let me explain this. What you see on the left is a spectrum, and you see these dark lines which are known as spectral lines. And these are spectral lines from a source which is stationary. For example, a sodium vapor lamp in the laboratory or a tube light in the laboratory. What you see on the right is the spectrum of the same sodium or mercury or potassium or whatever it is, and what you see is that these lines are shifted upwards and the wavelength is increasing upwards in this figure. Slipher interpreted this shift of the spectral lines to longer wavelengths as Doppler effect. That I'm sure all of you have heard of Doppler effect. We are familiar with Doppler effect in sound. I'll come to that in a minute. And what Doppler effect says is that if a source of sound or a source of light is moving with a velocity v, and if c is the speed of light or the speed of sound, then the change in the wavelength, fractional change in the wavelength, delta lambda divided by lambda, is equal to the velocity of the source divided by the velocity of light or the velocity of sound. And that can be seen very clearly here. If a stationary source emits a ray of light or sound wave, you have a crest, trough, and the wave expands spherically, symmetrically. The distance between two successive crests, which is called the wavelength, or two successive troughs, which is the wavelength, will be the same no matter from where you look at it. But if the source of sound or the source of light is moving, then as far as an observer towards which the source is moving is concerned, it will appear to that observer that the frequency of sound or light is higher or the wavelength is shorter. Whereas for an observer on the opposite side, it will appear as though the frequency is less and the wavelength is more. So this is the familiar Doppler effect. So what Westo Slipher concluded was that the shift in the wavelength of light from galaxies towards longer wavelength indicated to him that the clusters of galaxies are all moving away from us. Soon after that, a Belgian Catholic priest by name Georges Lemaitre built on Friedman's discovery. In 1927, Georges Lemaitre suggested that the recession of galaxies discovered by Westo Slipher might in fact represent the expansion of the universe as a whole. Nobody had thought of this before that. What does the expansion of the universe mean? I must point out here that very often the expansion of the universe, the idea of the expansion of the universe is attributed to the American astronomer Edwin Hubble, and this is not correct because this was first pointed out 2 years in advance by Georges Lemaitre. Now we all know that the universe is all there is. There is nothing outside the universe. So what do we mean by saying the universe is expanding? What is it expanding into? It can't be expanding into something because by definition the universe is everything there is. So this is not the correct way to think about it. So here is a little girl with her birthday balloon. So look at the picture on the right. The balloon is smaller, and plotted on the balloon are galaxies. And as she blows the balloon, you see the distance between the galaxies is increasing. So what we actually observe in the universe is that the distances between galaxies is increasing. And this conclusion would be true no matter in which galaxy you are. It is not special to us. So we have to conclude the expansion of the universe means that the space itself is expanding. So that is the correct way to think about it. It is not that the universe is expanding into something, but space itself is expanding. Here is a famous cartoon from a book by George Gamow published in the late 1940s called The Creation of the Universe. And once again, there is this balloon. And in this model, the universe, in Einstein's theory, is like the surface of a balloon. And this is a three-dimensional balloon whose surface is two-dimensional. The universe is three-dimensional, therefore we are talking about a four-dimensional sphere whose surface is three-dimensional, which of course we cannot visualize, so the pictures are drawn in one dimension less. So as the balloon expands and as the universe expands, all distances increase, as shown in the picture on the right. So you see as the balloon gets bigger and bigger, all distances get stretched. This is known as cosmological redshifts. So as the universe expands in size, all distances increase. Distance between any 2 points in the universe increase. Waves get stretched, the distance between two successive crests gets stretched. And so another way of saying that is that the wavelength has increased as the universe expands. So Georges Lemaitre pointed out in 1927 that for small redshifts, you are allowed to think of it as Doppler effect. But it is really not Doppler effect. It is really the stretching of distances due to the expansion of space itself. Now I must tell you that this paper was also sent to Einstein for refereeing, and Einstein wrote a very rude postcard to Georges Lemaitre saying your mathematics is good, but your physics is abominable. And of course Einstein was profoundly wrong. Georges Lemaitre also pointed out that if the universe is expanding in a uniform manner, then the velocity with which a cluster of galaxies is moving away from us will be proportional to how far away it is. A cluster which is twice as far away from us will move away from us with twice the velocity. A cluster which is 4 times further away will move away from us 4 times faster. This is a prediction that he made based on Einstein's theory. 2 years later, Hubble and his associate Humason wrote their famous paper in which they proved this. So here is their plot. What is plotted on the y-axis of this figure is the velocity or the speed with which a cluster of galaxy is moving away from us. As Hubble put it, all clusters are moving away from us as though there is plague on Earth. That is the word that he used. So what is plotted on the y-axis is the speed with which clusters are moving away from us, and what you see on the x-axis is the distance away from us. And just to give you a feel for it, nearby clusters of galaxies are moving with a modest velocity of 2000 kilometers per second. Now you will say, what do you mean by saying modest velocity of 2000 kilometers per second? I call it modest because if you look at the faraway clusters, they are moving away from us at a speed of 40,000 kilometers per second. Very difficult to comprehend, isn't it? But please notice that this is a linear relation. This is what Georges Lemaitre had predicted, that the velocity will be linearly proportional to how far away it is. Now that we know that the universe is expanding, we have to ask 2 questions. One is, how fast is it expanding today? Secondly, what is the present age of the universe? If you see a running race, a marathon going on, surely the faster guys will be farther away and the slower guys will be nearer the starting point. You can ask, when did the marathon race start? In a similar fashion, you can ask, what is the age of the universe? Now, What I've shown here in these arrows, look at the red arrows. When the universe was small, the red arrows are long. The universe is expanding very rapidly for reasons that we will come to. But I want you to appreciate the fact that the rate at which the universe will expand depends upon its age. Why? Because as the universe expands, look at the picture on the right, universe is filled with matter. Every part of the matter attracts every other part of matter due to Newton's law of gravity. So the expansion of the universe will slow down, very much like a stone thrown up slows down because the gravity of the earth is trying to pull it back. Initially the stone will move very rapidly and then it will slow down. Therefore, in a similar fashion, the expansion of the universe, you expect it to decrease, expansion rate, you expect it to decrease as the universe ages. Okay, today we are 2024 AD. What is the expansion rate? The expansion rate is the following. Look at the bottom there. Imagine there is a cluster of galaxy which is 1,000,000 light years away from us. What astronomers were able to conclude some 20, 25 years ago is that that cluster of galaxy is moving away from us with a velocity of 25 kilometers per second. Another cluster, which is 2,000,000 light years away from us, is moving away with a speed of 50 kilometers per second, and so on. So it is in this sense I said that the velocity of recession is proportional to the distance. So today we know the expansion rate. The expansion rate was very contentious for 100 years. According to some people, the universe was younger than your grandmother. Okay, so this controversy was only settled about 20 years ago. We now know the expansion rate of the universe to within about 8% or 10% accuracy, which is pretty good. Now, the second question we can ask is, when did this marathon race begin? In other words, what's the age of the universe? Well, the conclusion is that our expanding universe is roughly 13 billion years old. If you want to say 14 billion years, I will not argue with that. But it is 13 billion years to an accuracy of a few percent, which is pretty good. More precisely, there was a big explosion 13 billion years ago and the expansion began. If the universe is expanding, it must have been much smaller long time ago, and gravity would have been much stronger. So in order for it to expand, some violent event must have taken place. We have given it the name, the Big Bang. So something happened. We'll come to what this Big Bang is in a little while. But now we have to ask the following question. Was the beginning of the expansion of the universe same as the beginning of the universe itself? Well, we just don't know. Now let's go back to Georges Lemaitre. He argued that if the universe is expanding today, then if I run the movie of expansion backwards in time, the universe must have been smaller and smaller and smaller in the past. And if I extrapolate it sufficiently back in time, then the universe would have been just as big as an atom. It would have been incredibly small, incredibly dense, and incredibly hot. Now, did the universe really begin as small as an atom, which we call as the primeval atom? Well, if so, then the early universe would have been a veritable fireball. If I compress a gas, it will get hotter and hotter and hotter. So if I compress the whole universe to the size of a ping pong ball, naturally it will be incredibly hot, a veritable fireball. How hot would it be? I can use Einstein's theory of relativity to estimate the temperature of the universe when it was 1 second old. And the temperature would have been 1,000,000 degrees, one followed by 12 zeros. If I missed out 1 or 2 zeros, it doesn't matter. Now, did the universe evolve from such a hot, dense beginning? Is there any evidence for this? The answer is a resounding yes. So let's discuss that now. In 1920, Sir Arthur Eddington in Cambridge University argued that stars shine because in their dense, hot interiors, at temperature about 15 million degrees, they are converting hydrogen to helium. Of course, everybody laughed at him. But Eddington was convinced. It took almost 100 years to prove that he was right. But Eddington was convinced that there was no helium in the beginning. The helium must have been synthesized in the stars, in the hot ovens at their centers. Now, we will discuss a similar synthesis of elements in the early universe. George Gamow was a young, brilliant Russian theoretical physicist who had emigrated to America, and he was the first person to appreciate the significance of Georges Lemaître's primeval atom concept. He suddenly realized that there was another place and another time where Eddington's idea would work. Another place and another time, like the interior of stars, was the early universe. So in 1940, George Gamow advanced the idea that the elements were synthesized in the early universe, when it was very hot and when it was very dense. What were the elements? Let us concentrate on the light elements. I have shown here the first four light elements, and hydrogen consists at the center in the nucleus of one positively charged particle, which is called the proton. The next heavier element is deuterium. It has two particles in the nucleus, one positively charged particle and one neutral particle, which is called as a neutron. The next heavier element is helium-3, which has two positive charges and one neutral particle, and the more familiar helium has two positive charges and two neutral particles, and so on. So these are the elements. Now Gamow and his collaborators calculated the abundance of deuterium, helium-3, helium-4, lithium-7 based on this idea that when the universe was hot and dense, you can convert lighter elements into heavier elements. And I won't belabor this point, but I would like you to appreciate that the abundance they calculated of deuterium, helium-3 and helium-4 and lithium-7 agreed spectacularly well with the observed abundance of these light elements. So this was a tremendous success for the idea that the universe evolved from a hot primeval fireball. I would also like you to appreciate that the synthesis of deuterium, helium, lithium took place when the universe was precisely 180 seconds old. How do I know that? I wasn't there around that time. Well, that is the power of science. If you try to synthesize an element when the universe is too hot, then the heat will break up whatever you have synthesized. If you wait long enough, then the universe is expanding so rapidly, protons and neutrons will never collide with each other to form heavier elements. So it is a competition between formation and destruction. And that was available only when the universe was 3 minutes old. Okay? So all the deuterium in the universe that we see today, all the helium-3 and helium-4 in the universe today was synthesized when the universe was 180 seconds old. Now Gamow and his collaborators, Alpher and Hermann by name, pointed out in 1940s that if Georges Lemaître's idea was right, then there could be another evidence for the evolution of the universe from a hot Big Bang, a second piece of evidence. The universe must still be filled with the cooled relic of the primeval fireball. The universe was small, it was filled with hot radiation, and as the universe expanded, since there is nothing outside the universe, the radiation cannot expand, and just as a gas cools When it expands, that is how you cool things in your refrigerator in the kitchen. Similarly, radiation will also cool. So if the universe was as small as a ping pong ball, 3 or 4 centimeters in size, it would have been very dense and very hot. If so, the relic of the primeval fireball must still be there in our universe. George Gamow predicted in 1940 that the present temperature of the relic of the primeval fireball, the cooled radiation, will be just a few degrees Kelvin or somewhere around minus 270 degrees Celsius. So this was a clear prediction made around 1940. Now, in the early universe, there were no stars, there were no galaxies. In fact, there were no molecules, there were no atoms, there wasn't even nucleus of the atom. It was so hot that everything was broken up. All you had was a collection of electrons, protons and neutrons and radiation bouncing off each other in perfect thermodynamic equilibrium. What kind of a radiation will they emit? The radiation they emit will be the same kind of radiation that will be emitted by a hot iron rod or the filament of incandescent bulbs. Many of the young people here won't even know what I mean by incandescent bulbs because they've all been replaced by LEDs. So this is the radiation emitted by hot bodies. And the spectrum of the radiation, intensity on the y-axis, wavelength on the x-axis, is a bell-shaped curve which is described by a law which is known as Planck's distribution. So the spectrum of radiation emitted by hot body is precisely known by us. So here are some examples. What is plotted is the spectrum of radiation emitted by hot bodies at different temperature. What is plotted on the y-axis is the intensity of the radiation. What is plotted on the x-axis, increasing to the right, is the wavelength of the radiation. The outermost curve is an object heated at a temperature of about 6,000 degrees, like the surface of the sun, and the innermost curve is an object at a temperature of 100 Kelvin. I could have plotted a body which is heated to 1 billion degrees or 1 million degrees, and they will be sitting on top of one another. What I want you to appreciate is that the wavelength at which the maximum intensity occurs, which I have shown by red line, depends upon the temperature. You notice that when the object is hot at 6,000 degrees, the maximum intensity occurs at a shorter wavelength. When the object is cooler at 100 degrees, the wavelength at which the maximum intensity occurs at a longer wavelength. And that is given by a very simple formula which says the wavelength at which the intensity is maximum is 0.3 divided by the temperature. So if the temperature in the bottom is 1 million degrees, the wavelength or the frequency will correspond to gamma rays. If the temperature in the bottom here corresponds to a few degrees Kelvin, the maximum wavelength will be in the microwave region, a millimeter or a few millimeters in size. So what we are saying is that as the universe expanded, since all distance scales are stretched, which is the cosmological redshift, the primeval fireball would have cooled and the relic will now be still present in the universe, but the temperature of that radiation will be just a few degrees Kelvin and the wavelength at which it will peak will be in the microwave region. So, the ancient Chinese saying, one picture is worth 10,000 words. So what I am showing here is the early universe, hot and dense, filled mostly with gamma rays, and as the universe expanded 14 billion years later to a very large size, it should be filled mostly with microwaves. This is a prediction. In 1964, Arno Penzias and Robert Wilson, working in the Bell Telephone Company, discovered the relic of this primeval fireball that fills the universe using the telescope, radio telescope that is shown in the central picture. So this relic of primeval fireball was found and its temperature was 2.73 Kelvin, just as it was predicted by Gamow. He had predicted 8 degrees or something like that. It was roughly 3 degrees. Now what is shown here is a representation of the entire sky in all directions, and the color indicates the temperature, in this case 2.73 Kelvin. You notice that this radiation fills the entire universe and the temperature is the same everywhere. This is not the radiation emitted by stars and galaxies and nebulae. That is there. This is the radiation that is there between the stars, between the galaxies, between the clusters of galaxies. This is the relic of the primeval fireball. This radiation is present everywhere, and it has the same intensity and temperature everywhere, which is a characteristic of radiation from a hot body. Now, if the cosmic background radiation is indeed the relic of the primeval fireball, then its spectrum, intensity versus wavelength, must be precisely given by Planck's law. Now, you can't measure all the wavelengths from the Earth because the Earth's atmosphere absorbs the radiation. So a satellite known as COBE, Cosmic Background Explorer, was launched in 1989 to precisely determine the spectrum of the cosmic microwave background radiation. Because what Penzias and Wilson measured was the intensity of the radiation at 1 or 2 wavelengths. Now you want to measure the intensity at all wavelengths and confirm that the spectrum is indeed given by Planck's law. You want to confirm that the spectrum is given as shown in the picture over there. And the COBE satellite measured this, and here is the spectacular plot. What is shown as the blue curve is the theoretical distribution of a hot body at a temperature of 2.73 Kelvin, and the red crosses are the experimental points. This is the most spectacular agreement between theory and experiment that I know of in any branch of physics. So this was a sensational confirmation of the prediction that was made by George Gamow. And so the Nobel Prize for Physics was awarded in 1978 for the discovery of the cosmic microwave background radiation to Penzias and Wilson. Now once again, this is the relic of the primeval fireball that fills the universe, and there is therefore strong evidence to support the hypothesis. Remember, we made a theory of a theory. The theory was that the universe evolved. Now we are looking for proof of that. Now I submit that there is a strong evidence for this evolution. There is first the cosmological nucleosynthesis. The abundance of deuterium and helium and lithium agrees spectacularly well with the cosmological nucleosynthesis model, and the relic radiation has the black body spectrum that was predicted. So I submit to you that these two discoveries give a strong, provide strong evidence for the hypothesis that the universe has indeed evolved from the beginning. But there is a problem. Now, without doubt, as I said, in the very early universe, there were no stars, there were no galaxies, there were no clusters of galaxies. There was just a soup of elementary particles and radiation. So, from this soup, somehow stars must have formed. Somehow galaxies must have formed. Somehow clusters of galaxies must have formed. Somehow the grand architecture of the universe must have evolved. So there is a great mystery here. How did, from a uniform soup, all these things arose? Now, there is a second problem. Did the large-scale structures arise first and then the small-scale structure, or the other way around? Did stars form first, and then they aggregated to form galaxies, and galaxies aggregated to form clusters of galaxies, and then clusters of galaxies aggregated to form this structure, or is it the other way around? We have evidence for both in nature. If you take a crystal, the way you grow a crystal in a laboratory is to take a small crystal and it becomes larger and larger and larger and larger. But if you go to a river in flood, you will find eddies there, small eddies, big eddies and bigger eddies. You find smaller eddies don't merge to become bigger eddies. Bigger eddies break up into smaller and smaller eddies. So in nature you have this cascading occurring both from large scale to small scale as well as from small scale to large scale. So the big mystery here was, which is the way our universe evolved. Now I am happy to say that we have a pretty good understanding of this. Well, earlier I said that the temperature of the microwave background is the same everywhere as seen in this picture. Well, it is not quite the same everywhere, it is almost the same everywhere. And it took quite an effort to determine why almost. There you see it. It took 10 years of observation by this COBE satellite to establish that some places the radiation is hotter, redder, some places it is cooler, which I have indicated by blue here. But it is a ever so small inhomogeneity. It's only 1 part in 100,000. That's why it took 10 years of observation by the COBE satellite to establish this inhomogeneity in the temperature of the microwave background radiation. Why? The reason is the following. If I compress a gas to a higher density, it will be hotter. If the gas expands, it will be cooler. So there are two ways of interpreting this. You can say some regions are hotter, some regions are cooler, or I can also say some regions are denser, some regions are little less dense. So this is evidence for density fluctuation. So slight variation in the temperature of the relic radiation suggested fluctuations in the density of matter. We are talking of density of matter when the universe was 300,000 years old, long time ago. Okay? That's far cry from stars and galaxies and clusters of galaxies. But at least there was some hope that it is not entirely homogeneous. So then the second question was, where did these density fluctuations arise? There must be some reason for it. Fortunately, a theoretical prediction came around 1980 as to why these density fluctuations arose. We won't digress into that. So finding this inhomogeneity in the density in the very early universe gave us hope that someday we will understand how from this primordial soup stars and galaxies and clusters of galaxies form. I am happy to say that this problem is now well in hand. What astronomers have been able to do is do giant computer simulations using supercomputers. What you do is you have a box in which you have billions of particles which are interacting according to Newton's laws. The box is expanding, box is our universe, and you just let it evolve. And believe it or not, these structures are reproduced spectacularly well. So we now have a very good understanding that first the large structures formed, from which the smaller structures formed. And secondly, we understand how these structures form. The key to it is the following. If the box did not expand, these structures will not form. So the expansion of the universe is essential for the structures to form from a uniform soup. But I am not digressing that. Therefore, it's not surprising that in 2006, John Mather and George Smoot were awarded the Nobel Prize for the discovery of this inhomogeneity and also measuring the spectrum of the primordial fireball, the cosmic microwave background radiation. Now comes this difficult question. Why is the universe expanding? The first possible explanation came only in 1984. Alan Guth in MIT in Boston discovered that when the universe was 10 to the power minus 35 seconds old, 1 divided by 1 followed by 35 zeros, it could have expanded exponentially to an enormous size, from the size of a ping pong ball to billions and billions and billions of light years in size in a very, very, very short time. He showed that the universe could have doubled in size every 10 to the power minus 35 seconds. So it was an exponential expansion, not a power law expansion. Imagine the universe doubling in size every 10 to the power minus 35 seconds. And this exponential expansion is what we call is the Big Bang. We called it Big Bang long ago, but we now understand why the universe started expanding very, very rapidly. It is this exponential expansion. So let me explain this. What is plotted on the y-axis is a measure of the size of the universe. And what is plotted on the x-axis is the time. And there is 10 to the power minus 35 or 30 seconds. The universe expanded exponentially up to that time, and then after that it expanded as a power law. In other words, the universe continued to expand, but it is now decelerating. Gravity is pulling matter back in again. So there is time on the y-axis, and this is space. So here is the representation of the two-dimensional universe, because that's all we can visualize. And what you see in the bottom is that exponential expansion which occurred for a very, very, very short time, and that is presumably the Big Bang. Now what caused this exponential expansion? Physicists think that something similar to vacuum energy could have caused faster than light expansion. Exponential expansion is an expansion faster than light. What caused it? This is what physicists think, astronomers think. Let me try to explain this. Unlike in classical physics that we grew up with, vacuum is just emptiness. There is nothing there. But that's not true in quantum physics. In quantum physics, emptiness is a lot of interesting things happening. Vacuum is very rich in physics. For example, there is energy associated with vacuum. And this energy is just like the energy of matter or the energy of radiation. This energy of vacuum is positive. But interestingly, the pressure of vacuum is negative, whereas the pressure exerted by matter and radiation is positive. When I try to pump a cycle pump, it gets harder and harder and harder. That's because the gas exerts, compressed gas exerts positive pressure. The gas has positive energy and exerts positive pressure. Vacuum has positive energy but exerts negative pressure. I don't have time to explain that to you. Please accept that statement. It's a pretty simple thing to explain, and it is in fact quite trivial, but please accept that statement. Now, in Newton's theory, only mass produces gravity. But in Einstein's theory, all forms of energy produce gravity, because E is equal to mc squared. So it doesn't matter whether you call it matter or energy. So energy doesn't have to be associated with matter. All forms of energy will produce gravity. Matter will also produce gravity. Now, in Einstein's theory, therefore, pressure is also a source of gravity. Why? What we call as pressure is that the energy per unit volume, that's all. If I compress cycle pump, what we call as pressure is simply the energy of what is below the piston divided by the volume below the piston, multiplied by 2 divided by 3. Let's not bother about the 2 by 3. Therefore, pressure is nothing but internal energy. Therefore, pressure will also produce gravity. Now, please remember this. Gravity produced by mass is always attractive. But gravity produced by pressure can be either attractive or repulsive, because the pressure can be either positive or negative. So depending on what kind of pressure you are talking about, gravity produced by pressure can be both attractive or repulsive. Now, since vacuum has negative pressure, vacuum energy produces repulsive gravity. Okay? So, please accept that statement and let us proceed. Now, as the universe expands, the energy per unit volume will decrease because the volume is increasing. This is why the universe decelerates. But energy density of vacuum is a constant, because as the universe expands, there is more vacuum and therefore there is more energy. So there is no dilution of the energy density of vacuum, unlike the energy density of matter or radiation. This is why this exponential expansion occurs. Unfortunately, I don't have time to elaborate on it. So, in case you understood it, it's fine. Otherwise, just accept the statement. Physicists think that what caused the exponential expansion at the age of 10 to the power minus 35 seconds was a phenomenon similar to vacuum energy. Not quite vacuum energy, but something similar to vacuum energy. Another way of saying that is the initial exponential expansion of the universe is an accelerated expansion when gravity acted as a repulsive force instead of an attractive force. So we now have a plausible explanation for why the universe is expanding. The repulsive gravity of vacuum energy caused the expansion of the universe. And this, because it's exponential, we call it a Big Bang. I mean, it expanded very suddenly. Was that the beginning of space and time? We don't know. Right now, the universe is not only expanding, it is accelerating. This discovery was made 24 years ago. What is shown on the y-axis here is the size of the universe, x-axis is again the time, and what you find is that the universe is now accelerating. When I throw up a stone, it will just slow down. Now, that's because gravity is pulling it. Suppose there is also repulsive gravity. Then the repulsive gravity will act against the attractive gravity. But if the blue arrow is smaller than the red arrow, then the repulsion will not be dominant. Gravity will still slow down the stone. But if the repulsive gravity is stronger than the attractive gravity, the picture on the right, then the stone will accelerate. The white arrow is getting longer and longer. Therefore, for the universe to accelerate today, the repulsive gravity must be dominant over the attractive gravity due to matter. So what we have is a Big Bang with a little push. So presently some repulsive gravity is pushing the universe. Not only that, this repulsion dominates over the usual gravitational attraction, otherwise the universe will not accelerate. Presumably this is why the universe is accelerating. Now physicists think that this acceleration today, not the one that occurred when the universe was 10 to the power minus 35 seconds old, the acceleration of the universe today is again related to something like a vacuum energy. We don't know what this is. We give it a name, vacuum energy. But what I want you to appreciate is the following. After 30, 40 years, astronomers produced this remarkable energy density budget of the universe. What you see is that matter and radiation together contribute only 27% of the energy density of the universe. The remaining 73% of the energy density of the universe, we don't know what it is. So we call it dark energy, we call it vacuum energy. Someday it will become clear what it is. So let's face the fact, we don't know what it is. But we'll give it a name. We'll call it dark energy, or we'll call it vacuum energy, or we'll call it cosmological constant. Call it what you like. We don't know what it is. The important thing for you to appreciate is 73% is larger than 23%, 27%. Therefore, cosmic repulsion is much larger than attraction due to matter and radiation. And this is why the universe is accelerating. So today, the repulsive gravity, due to whatever it is, we don't know what it is. This is one of the most outstanding questions of physics in this millennium. We don't know what it is, but we know that it is producing repulsive gravity, and that is dominating over the attractive gravity. After a while, attraction due to matter will become irrelevant, and vacuum energy will dominate, and the universe will expand exponentially like it did in the past. So what will be the fate of our universe? The universe will once again, like it did in the very early universe, expand exponentially. After 10 to the power 100 years, all the matter in the universe would have decayed by some process or other, and the universe will essentially be empty. So the future, distant future of the universe will be very boring compared to the distant past, when we synthesize the elements and all that. Everything will be undone now. So far we have discussed the evolution of the universe, past evolution and possible future evolution. Now I must go to the difficult thing, namely turn to the origin of the universe. And we asked the question, was there a beginning? Was there a beginning to the universe? Which in Einstein's theory means, was there a beginning to space and time itself? Now this question, as you know, is at the base of every religion and philosophy. But it was a meaningless question in science till quite recently. It was a meaningless question in science because there is no way to pose this question in a rigorous fashion. In science, questions have to be posed within the premise of science in a rigorous manner. This was not possible. Please remember that Georges Lemaitre and Georges Gamow talked about the beginning of the universe, but that was just an extrapolation. You are running the movie backward. Maybe the expansion began day before yesterday. You have no business to run the movie backwards till the universe was a point. Yes, we have found evidence of nucleosynthesis, the cosmic microwave background radiation. But you can extrapolate backwards to 1 microsecond, maybe even a billionth of a second. Because if you try to go before that, if you go to time of the order of 10 to the power minus 35 seconds, the densities and temperature you're talking about are so enormous that we cannot trust the laws of physics as we know today. So we have to be very modest in saying that yes, I can extrapolate the movie backwards to 1 microsecond, maybe even a billionth of a second, maybe even a billionth of a second, but not indefinitely. Pretty soon I'm going to run into a brick wall. But this question suddenly acquired a meaning in 1965 within the premise of Einstein's theory of relativity. And thus began the present revolution in astronomy. And the revolution started with Roger Penrose proving a very remarkable mathematical theorem concerning black holes, which are the end states of massive stars. But this is not the time to digress about black holes, but you all know that when we talk of black holes, we are talking of a situation where gravity is extremely strong. And it occurred to a 19-year-old young Stephen Hawking, a young student in Cambridge, that the very early universe gravity must have also been very strong. So he wondered whether Penrose's theorem has an application for the very early universe also. And so together Penrose and Hawking proved a very remarkable theorem. This theorem was mathematically exact and there are absolutely no approximations made. And what this theorem says is the following. Within Einstein's theory of relativity, the universe could have begun in a singularity or end in a singularity, or both began and will end in a singularity. Now I want you to appreciate that this conclusion was not based on any extrapolation. This is a rigorous mathematical result. So the question can now be asked, was there a beginning to space and time? The answer is yes, you can ask the question, and there is even a possible answer to that question. Space-time singularity is a mathematical term for a point in space and in time of zero volume and infinite density. If we extrapolate backwards in time, the expansion of the universe, which you are now allowed to do, the universe will contract to a point. Space and time will end there. Or if you want to move forward in time, space and time will begin there. So that would be the beginning of the universe. But we cannot extrapolate beyond the singularity and ask what was there before the beginning. You are not allowed to ask this question because mathematics doesn't allow you to extrapolate space and time through a singularity. Now, singularity in physics usually signals the breakdown of a theory. So a space-time singularity signals the breakdown of Einstein's theory of relativity. So you cannot trust a theorem that is proved within the premise of Einstein's theory of relativity, because the theory itself is breaking down. What I'm saying is, when the universe was extremely small, a million times smaller than an atom, when you're talking of a distance of the order of 10 to the power minus 33 centimeters, you cannot trust Einstein's theory of relativity. What you need is a quantum theory of gravity. Just as you cannot use Newton's theory of mechanics to describe atoms and molecules, similarly you cannot use Einstein's notions of space and time when you're talking of very short distances and very short time scales. You need a quantum theory of relativity or a quantum theory of gravity. But such a theory doesn't exist as of now. So if you look beyond Einstein's theory, what we are groping for is a quantum cosmology. Quantum cosmology doesn't exist, but people are working on it. There are models of quantum cosmology. According to these models, what is the history of space and time in quantum cosmology? According to almost the last paper that Hawking wrote with Jim Hartle, in quantum cosmology, there may not be a singularity like Hawking and Penrose proved in classical gravity of Einstein. In quantum gravity, the history of the universe may be like going along a longitude on the surface of a hypersphere. What do I mean by that is the following. Here is a sphere, globe. Here are latitudes and longitude. Imagine that going along the longitude is going along backwards in time, going forwards in time. Imagine that. So space and time, according to Hartle and Hawking, could be like the surface of the earth, but not in 3 dimensions, but in higher dimension. But here is a nice picture. The important thing for you to appreciate is the following. On earth, if you go along the longitude, north and north and north, you come to the North Pole. But the earth doesn't come to an end at North Pole. You can continue the earth beyond. So what they are trying to say is that time and space could be like the surface of a higher dimensional sphere. Therefore, there may be no edge to the universe. There may be no beginning in quantum cosmology. This is one possibility. One possibility in quantum cosmology, there may be no beginning at all. There is another intriguing possibility according to Stephen Hawking. Long time ago, Richard Feynman, one of the greatest physicists of 20th century, had a formulation of quantum mechanics in the following fashion. Suppose there is a particle here at one time and it is here. It could have gone like this, it could have gone like this, it could have gone this way, it could have gone that way, it could have gone any number of ways. Which way did it go? According to Feynman, it could have gone in all possible ways with different probabilities. And quantum mechanics tells you to calculate what is the most probable path it went from here to there. In a similar fashion, Stephen Hawking said that maybe what is the history of the universe? Well, it could have had every possible history. Which one? Well, different possibilities are different probabilities. But please remember, however clever people like Stephen Hawking may be or may have been, these are all at present only speculations. We can only speculate. Only time will tell what quantum cosmology is going to be like and what history of the universe it is. But let's assume for a moment that there was a beginning. I'll conclude in 2-3 minutes. If there was a beginning, it raises several uncomfortable questions. What was there before the beginning? Was the universe created out of nothing? Why is there something in the universe instead of nothing? Why should there be something at all? But if there was a creation, how did the creation happen? If there was a beginning from nothing, how did it happen? Was the universe created by quantum fluctuations? Now there is a difficulty there. The universe is full of matter and radiation. There is a lot of energy. Where did this energy come from? It is true, according to Einstein, you can convert matter to energy, energy to matter. But finally, where did the energy come from? Now, you can hypothesize that God created everything. But you are forced to ask, you are compelled to ask, is this hypothesis satisfactory? If there was nothing before the creation, why was there a God? And where was God till then? And what was he doing till then? These questions have been asked by philosophers. And who created God? So you see, just as I admitted science is not able to cope with this question, you can't escape by just hypothesizing that God created everything. Einstein once asked the following question: if there was a creator, did the creator have a choice regarding the kind of universe he would create? What do I mean by that? Did God create the universe with the laws of physics in such a way that complex life forms will emerge, consciousness will evolve, and I would be standing here talking about it and you would be sitting there listening to it? Because this cannot be an accident. So, or did God create an infinite number of universes, each with its own possible laws? We happen to be in one universe where the laws are what they are, and life could have originated, and complex life and consciousness could have evolved. So, astronomers are now talking about a multiverse. Our universe is one of an infinite number of possible universes. Now, if there was a beginning from nothing, you have to ask the very difficult question: how did the laws of nature come into existence? Did the laws govern from the beginning of the universe, or did the laws evolve later on? In 1932, Gandhi made a recording in London about God, a 5-minute recording in Columbia record. I have that record, gramophone record. There he says, the law and the lawgiver are one. According to Gandhi, God is this supreme law that governs the universe. And he says the law and lawgiver are one. But where did this law come from? Okay? Now, is the universe fine-tuned for complex life? This is a very serious question, because you see, our world is 3-dimensional. Now, the world could have been 2-dimensional, 17-dimensional, 25-dimensional. The charge of the electron could have been slightly different. The mass of the elementary particles could have been slightly different. Then atoms wouldn't exist. Atoms wouldn't exist. Chemistry wouldn't exist. Biology wouldn't exist. Life cannot exist. So in order for life to exist, you have to have all the things the present universe has. Is that an accident or is it by design? We don't know. Faced with these difficulties in recent times, deep thinkers like Roger Penrose have been talking about the concept of cycles of time and eternal universe, like in philosophy and religion. So here is Penrose's concept. The universe in the distant future will look very similar to the distant past. There will be another Big Bang, then another Big Bang, and so on. According to another possibility, the universe expands, contracts, there is another bang, another Big Bang, and so on. And there could be another possibility if there was only one bound. There was a previous universe and there was a Big Bang. Now, how do we choose between all these theories? Each of these theories have to make a clear prediction, which has to be tested observationally. And observations are the sole arbiters. There is no other possibility. That is the difference between science, philosophy, and religion. In science, there is no room for beliefs. You cannot say, I believe in this, or I have faith in this. Science does not permit you to do that. The great French mathematician Laplace wrote his famous book on celestial mechanics, and he presented a copy of that to Emperor Napoleon, who happened to have been a student of Laplace when Napoleon was young. And so Napoleon had looked through the book. He called Laplace and said, Professor Laplace, why is there no mention of God in your treatise? Laplace replied, Sire, I have no need for that hypothesis. The ancient Chinese and Greeks argued that it is meaningless to talk of a beginning, that one should only attempt to describe the universe as it is with rational thoughts. But as you know, most religions postulate that God created everything. But cosmology in our subcontinent predates religion, predates Hinduism, Buddhism, all religions. It dates back to pagan times. And let us ask, what does the oldest of the written document, Rig Veda, say about this? Please remember the Rig Veda was transmitted orally for more than 1,000 years or more, and then only it was written down. So here is what Rig Veda says. There was neither non-existence nor existence then, neither the realm of space nor the sky which is beyond. Whence was it produced? Whence is this creation? Gods came afterwards with the creation of the universe. Who then knows whence it has arisen? Whether God's will created it or whether he was mute. Perhaps it formed itself. Perhaps it did not. So, Vedas don't give us an answer. So let's return to science. Was there an evolution? There is strong observational evidence to support the idea of the evolution of the universe. According to Penrose and Hawking, there can be beginning within the premise of Einstein's theory. And the beginning will be a singular beginning. But unfortunately, that is precisely the circumstance when Einstein's theory breaks down. So one will have to wait for quantum cosmology. At present, we do not have such a theory. So within the premise of science, the question still remains difficult to pose, let alone answer, at present. Religion seems to offer a definitive answer to this question. There is a creator. There is just a definitive statement. But please remember that this hypothesis can neither be proved nor be disproved. And therefore, according to Bertrand Russell's philosophy, it is not a very meaningful theory, because a theory should be either provable or disprovable. Now, the theory about a creator can neither be proved or disproved. On the other hand, a scientific theory is considered credible only if it is falsifiable. We always think scientific theory should be proven. Of course it should be proven. But even more importantly, the theory should say, if such and such is true, then this theory is wrong. At the moment, we just don't know. So let us ask so many question marks on the top. Given enough time, centuries or millennia, are we likely to find the answers to these questions? Or are these questions beyond the reach of the human mind? I think it's perhaps wise to be humble about this. Humans have been around only for a very, very short time, just a couple of 100,000 years. Surely the human brain will evolve further as it has evolved in the last 10, 15,000 years. So it should not surprise us that at present we are not able to ask and answer all the questions. But please remember that we know so much more about nature than humans in antiquity. So someday the questions that are meaningless today may acquire meaning within the premise of science. So someday science may have an answer to this question. Was there a beginning to the universe? So how do I end this talk? Religion has no answer. Science has no answer. So I think I would like to go back to John Milton, 1666, and his great poem, Paradise Lost. I will read it for you. Perhaps to move his laughter at their quaint opinions wide. Hereafter, when they come to model heaven and calculate the stars, how they will wield the mighty frame, how build, unbuild, contrive to save appearances. I thank you very much for your attention.
My name is Suraj. I have a very elementary question. We always talk about time and the expansion of the universe, starting with 10 power minus 35 seconds, goes on to the age of the universe being in billion years. Now, what is this reference of time? Because the moment we talk about seconds, minutes, and years, it has no relevance outside the earth itself. So, how are we hypothesizing? Is it with respect to us, is what we are talking about this time?
Let me be very frank. Having given this lecture and received a wonderful applause, I have no clue what is space and what is time. I'm being very, very honest about it. And I don't think very many people in the world know that either. Philosophers have been arguing for hundreds of years. What is space? We think of space as emptiness where we put chairs and tables and buildings and so on. But Immanuel Kant was the first person to ask the question, but is the concept of space and time meaningful if there is no universe? And that is what Einstein's theory of relativity is. Einstein's theory of relativity says space and time itself, it has no meaning if there is no matter. And if there is, so one is left-hand side of the equation, one is right-hand side of the equation. Now, with regard to your question, you are absolutely right. The unit of time we are using is based on how we measure time. But what time is, I have no clue. What I do understand is intervals of time. Okay. I can say this happened before, this happened afterwards. But I don't know what time is. One possible answer is time is that attribute which tells you that the entropy is increasing. So that is the only way we know in physics of defining time. That is, if people talk of arrow of time, which way is the arrow pointing? It is pointing in the direction where the entropy is always increasing. So I am sorry to give a very vague and unsatisfactory answer that reflects on my total ignorance on this. I've spent years worrying about this. I have no answer.
But that was still a wonderful answer for us. Thank you.
Sir, I have a question about the model which you said where the universe expands and then shrinks and then it starts again. So what would be, at the moment, as you said, the universe is accelerating. So what would be the theoretical model for why the universe would shrink again?
These are models. Our universe, unless there is some physics that we discover we don't know, is not going to contract again. It's going to expand forever and become truly infinite. But we didn't talk about this dark energy till 25 years ago.
Right.
So we don't know in another 1,000 years what new physics they will discover. Just as we discovered vacuum energy which is causing repulsive gravity, they may discover a new kind of matter which produces attractive gravity. So that can make the universe shrink again. But if you ask, the universe as we know today and the physics we know today cannot contract again. But then we have to be modest about it. We don't know in the time. See, we are talking of 10 to the power 100 years. And our physics has evolved in the last 2,000 years or so. Right? So I believe we should be a little bit humble about it.
Right.
That's why I would not like to dismiss any of these things.
Okay. Thank you, sir.
So my question is like in relation with the multiverse theory. So if there are multi-universes, then when did they start? Did they start at the same time our universe started, or did they start before or after? And how did they start?
It's a very interesting question. Imagine you're blowing a birthday balloon. And imagine that the rubber or whatever the balloon is made of is not of uniform strength. In some places it is weaker. So as the balloon is blowing, suddenly in one place a new balloon pops up, another new balloon pops up, and that expands and another balloon pops up. Okay? So the idea of eternal multiverse is that the universe is, even now, universes are being created and created and created. So it's not over. There's an infinite number of branches which are being created all the time. Okay, so the creation of universe is still going on. If you believe in the multiverse model, there is no other alternative. You cannot say it's all been done in the past. Of course, the model itself, we don't know if it is meaningful or not. But according to that model, it's still happening.
Namaste, sir. Is there a universe where Creator God lives? Creator God lives. Is there a universe?
Is there a universe where the created God lives?
Your guess is as good as mine.
So, when you started out in your career where you had to start exploring these things, I'm sure it would have been very hard to understand and articulate abstract things like multi-universe or string theory or quantum, all these. What was your mental models when it came to explaining these things to yourself and then to others? And second question is, what keeps you up at night these days? What are your bigger questions you're trying to answer?
I think as for the second question, it will be too pompous of me to say what keeps me awake, because there are questions. For example, if you try to ask what was there before the beginning, then after a few seconds you sort of go crazy, because you cannot hold the question in your mind, because there is nothing to relate it to. If you say, how did something come out of nothing, you cannot imagine what is nothing, because we don't know what nothingness means, right? These are just words. So I keep awake thinking about totally meaningless things like this. Well, the way I visualize things, of course, if I were giving this talk to PhD students, I'll be writing equations. Now that is one way to hide your ignorance. So the way I formulate my own ideas is by giving talks like this to people who know even less than me. Particularly if I talk to school children, it's very difficult because they will call you a bluff. You can't use mathematics. And so the challenge is, can you explain to your neighbors' children So in trying to do that, you discover that you don't know. Okay, we are talking at a high level, you think you know. But when you talk to a small child, you discover where you get stuck. You get stuck in your explanation because that's where you don't know. So it's a slow process of things coming into focus. So I don't think, well, that is not true of the great people, right? That's what we call as enlightenment. That is true for whether it is in religion or science or whatever it is. But for ordinary mortals, it's a very slow, gradual things coming into focus, maybe right, maybe not right.
So you said that new multiverses are even coming now and then, right? That they are getting originated or a thing. So if we can study how they are coming, then we can easily get to know how our universe came, right?
You have to first, finally, you have to go to a point when there was nothing, isn't it? So why do you think that our universe was the primordial universe?
Sir, but was it the primordial universe?
I don't know. Well, suppose if there were infinite number of universes, like I showed pictures of, and we are somewhere there. So there is nothing special about us.
Sir, so theoretically, if we travel far enough, we will be able to study how it all began.
No, why?
Because we might reach a point where a new universe is getting originated.
No. No. That's an interesting point. But you see, the universe that we see, even with the largest telescopes, is only 14 billion light years across, because that is the distance from which light could reach us in the age of the universe. But that doesn't mean that the universe is only that big. The universe is much bigger. Remember, the universe expanded faster than light.
Okay.
So you will never be able to reach the boundaries of our universe, traveling even at the speed of light, to find where the other universe is.
So, but
The only way it can happen is if two bubble universes collide, and like soap bubbles collide and coalesce. But these are all wild speculations at the moment. You see, the point is we are in a place in science today, in cosmology at least, we have reached a point where you can only speculate. And if Stephen Hawking speculates, people will listen. If I speculate, they will say this is nonsense. But it is just speculation. But that I am not putting down speculation. That is always the case. When you reach the limits of your knowledge, you speculate. And then then there is a breakthrough. The breakthrough always occurs with a new experimental discovery.
sir, so
Answer to your question is I have no clue how to answer your question.
You talked about the multiverse, then do the same laws of physics hold good in a multiverse, or do you think there is some kind of a change in some multiverse?
Well, we don't know. So that is the question that I posed. That is, we don't know if the laws of physics would be the same. In fact, even in our universe, we don't know if the laws of physics will be the same everywhere in our universe. We only know that to the extent that we have been able to sample the universe, the laws of physics seem to be the same. The laws of physics are the same in the most distant quasars, the most distant galaxies. That doesn't mean the laws of physics will be the same elsewhere in the universe. As to the other universe, that is the question that I pose. But if the laws of physics are not what they are, then there cannot be life in the universe, let alone complex life and consciousness. That is the big dilemma. Why is the universe so there is a principle that people have stated, it's called anthropic principle. The universe is as it is because we are there. By that they mean, in order for us to be there, these must be the laws of physics, this must be the charge of the electron, this must be the mass of the neutron, and this must be the value of the Newton's constant of gravity. That is really not saying much. It has been elevated to anthropic principle. It is not a principle or anything like that.
in different parts of, so that could be, that laws of universe could be different in our own universe.
Yeah, it could be different. Yes, it could be different.
Hi, Professor. You mentioned about Kobe satellite, which took 10 years to prove a particular theory. If that same thing has to be proved today, is it going to take lesser time? More importantly, while the universe is expanding at an accelerated pace, is our understanding also getting accelerated through technological advancement? Are we getting better and better and faster to understand?
Whether it is leading to accelerated understanding, I don't know. But whether we are acquiring knowledge at an accelerated pace, the answer is yes. For example, after the Kobe satellite, the next satellite that was launched, it was called WMAP, was able to produce a much more refined map of the anisotropy in less than a year. So improvement in technology does make a difference in accelerated acquisition of knowledge. But whether it results in accelerated understanding, that I don't know. I would not say so.
One suggestion I have for you is, if you've watched Spider-Man and the Multiverse of Madness, it's great. Otherwise, please take the trouble of watching it. It's called Spider-Man and the Multiverse of Madness. So if you see, a lot of the children came up with multiverse questions because I think they've watched that.
Oh,
but it's a very exciting movie they made, and they have touched in parts about what you spoke. So that's one thing I wanted to tell you. And other thing, sir, is if there are children of, let's say, her age, 9th and 10th standard, what are areas that are exciting to study in or research in now, how we can shape their thoughts?
So I will answer the second question with utmost seriousness to the young people. Stay away from cosmology. No. You see, this is all for retired people like me. Seriously, unless you're going to do some experimental work to find some new fact. Science is most exciting where experimental discoveries are producing new facts. So if I were her age, there is no doubt in my mind that I would be working on evolutionary biology. There is simply no question. Because if you ask which are the subjects where knowledge is most primitive, those are the areas where there is room for ideas. If you take many branches of physics, physics has become such a sophisticated subject that but there are, for example, material science is an area where every year people are discovering incredible things. See, all these things that I talked about, all these great advances in astronomy would not have been possible if it were not for progress in technology and material science. Almost entirely it is due to that. So I would say some of the most exciting areas of science today are, see, there are other subjects like what is consciousness. Of course, it's a very exciting subject, but it's not the subject that young people should go and work on. You should work on things which are very concrete, exciting discoveries, making new predictions, which leads to new experiments and so on. So I always tell students, don't work on cosmology. If you want to work in astronomy, if you ask me what would I work on, if I were your age, I would work on the exoplanets, planets around other stars. Because suddenly we realize that we have no understanding of the Earth, how the Earth was formed. Tomorrow somebody is going to contradict me, but my own feeling is, as I try to read about it, we don't understand much at all about how the Earth, how the planets form. So that's a very exciting frontier of astronomy.
How technological advancement have improved the work in astrophysics, sir. I would just ask a question that, do we have sufficient data to be fed in an AI model to get the answer? Because in your talk you told that few of the questions are out of reach of human minds, but there is a AI which can answer our questions, and if yes, are the works going on?
A very great man called Noam Chomsky. He works in MIT. He is now 90 years old. He's a great expert on languages and things like that. He said recently, a 2-year child knows more than the greatest AI models that you can compute, okay? So the answer to your question is emphatic no. Absolutely emphatic no. Because AI can, what is AI? It is merely searching the database which you have created. But you will, if you take Roger Penrose's theorem, or if you take Einstein's general theory of relativity, in thousands and thousands of years, computers cannot come up with that theory because it required an idea. So in order for that to happen, what we call as intelligence must transcend biological systems. If intelligence can be outside of biological systems, for example in machines, then what you say can happen. Since you can make more and more complex machines in an accelerated fashion, the intelligence of machines can just become much greater than, but we don't even know what intelligence means at the moment. If we really ask, what is intelligence, I think we'll have a hard time explaining it to a child. Between ourselves, we'll bluff by using fancy language. But you have to ask the question, can whatever that intelligence is, see, intelligence in some ways is related to consciousness and language. You cannot have conceptual thought without language. The language is the greatest creation of the brain. Okay? So we have no idea whether this can occur outside of biological system. So till then, I would say quite confidently no.
I have one small thing that is pertaining to the Indian theology and the scriptures and the epics what we have. So there, I find a lot of similarities where a lot of hidden information is there with respect to the cosmology. If we have to drive some kind of a similarity, what the science has still not understood. So how do we go about connecting our own scriptures and epics into this science, because we don't come from any kind of a mathematical model.
See, knowledge evolves. There is no such thing as Indian knowledge or Greek knowledge or Babylonian knowledge. Okay, so to me, I take off my hats off to people who thought about this thousands of years ago. But if I want to go forward, I would not go and look at something that was written 2000 years ago. When they did not know the earth was round, they did not know why the sun rises and goes this way. The sun goes around the earth. Stars go around the earth.
No,
that's what people thought, right?
Yeah. But it could be that we are not...
But please let me complete. There are certain things that people thought about, like what is reality? Is there something beyond physical reality? What do we mean by mind? Questions like that, I would say, something people thought about 2000 years ago could be as interesting and meaningful as something we think about today. But when it comes to things like the physical world, I would not pay much attention to. Aristotle thought gas rises because it is good, stone falls down because it is evil. They didn't know such a thing as the gravity. Okay, so people ask me all this time, it's all there in the scripture. Tautology. See, trees die, new plants form, seasons come and go, cyclical. So it is obvious, therefore, in mythology, there is creation and destruction of the universe, cyclical, universal. These are all very obvious things. So one should not, with the hindsight of present day wisdom, you are attributing a lot of things to what people said. So I would say that I would not say there is anything worth learning about contemporary cosmology by going back in time. That doesn't apply just to you are singling out our scriptures. There were people, ancient people in China, Babylon, Egypt and other places who thought. I would say the same thing applies to everything. Nothing, nothing
But I
special.
beg to differ. I beg to differ on this
Yeah,
point.
fine.
But one thing is, if you say, if at all it is there, if I try to drive some connection between science and spirituality, which would be the right forum to talk this and then present it? Is that one simple question which I wanted?
Anyway, thank you very much. This is a scientific lecture.
No, that's
Anyway, we appreciate, sir. We appreciate.
Thanks again for your lecture series on ASI channel on YouTube. It's
thank you.
really good.
Thank you.
I've not completed them, but they're really good. I'm kind of replaying them and looking at them. Very quickly, my question would be this. I don't know if you've heard of this book called We Have No Idea by two cosmologists from Stanford. I don't remember their names. But they question, one of the early questions, I've not completed the book too. It's pretty pithy. It goes into particle physics, quantum mechanics and stuff like that. So, but then they mention that we have no idea. The title of the book very clearly points at mass and gravity. They say the concepts of gravity and mass is not as clear. So can you throw some light on how, are there any inconsistencies or I don't know what fallacies within gravity or mass that they actually draw attention to that fact in the book? So,
I must read the book to respond.
Yeah, but in your experience and your understanding, are there limits that you see at mass?
All I know is that
the Higgs boson, for example, with mass, they talk about the Higgs boson, right? It was theoretically predicted long time back, and then they discovered the Higgs boson.
No, what has that got to do with gravity?
No, similarly they talk about, I forgot, I've been reading it for a while, but I don't, so basically they say there's a challenge, they don't understand it.
Maybe, but the number of things we don't understand far outnumber number of things that we do understand. So,
Yeah.
As we expected, this talk by Professor G. Srinivasan has started this year's Dussehra Lectures Series 2024 with a bang. This talk by Professor G. Srinivasan enlightened us with a fundamental understanding about our universe. No doubt, it has definitely left a long-lasting impression, sir, on you, and also will be remembered for long time to come. On behalf of JNP and audience here, I wholeheartedly thank you. Thanks, Professor G. Srinivasan, for starting this lecture series in a most glorious way. Thank you very much for your delighted lecture, sir. I also thank all the audience, including our REAP students who are present here, and all the other students of our non-formal academic courses that JNP runs, for attending this talk. And thank you everyone for being with us today. Thank you.